All right, this lesson is on sections 4.3 and 4.4, logarithms and laws of logarithms. The exponential function f of x equals b to the x, where b is greater than 0 and b is not equal to 1. We've talked about before, exponential functions are 1 to 1. So if b is greater than 1, it's growth, so I'll graph that. So this is what an exponential growth function that has y equals b to the x, where b is greater than 1 looks like. The domain is negative infinity to infinity, and it is 1 to 1. It passes the horizontal line test. So since it's 1 to 1, it has an inverse function. And the inverse of the exponential function with base b is the logarithmic function base b, written inverse of f equals log base b to the x. If you have y equals b to the x, then that's the inverse. Okay, so let's just look at that before we get any further. So hopefully you find graphing y equals 2 to the x not too bad. I'm going to put a few negatives in. So like if x is negative 2, then y equals 2 to the negative 2 means 1 over 2 squared. That's what a negative exponent does. So y is 1/4. Okay. If x is negative 1, then that means that y equals 2 to the negative 1, which is 1 over 2. If x is 0, 2 to the 0 is 1. Anything to the 0 power is a 1. Now we're going to get positive x values. If x is 1, y is 2. And if x is 2, y is 4. And if x is 3, y is 8. And if x is 4, y is 16. So as x goes more and more negative, the y is approaching 0, if you remember that end behavior. So there's a horizontal asymptote at y equals 0. When x is negative 2, it's 1/4. When x is negative 1, it's 1/2. Y-intercept is 1. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. And you get this backwards, or is the right side correct, J, looking graph. That's an exponential. Well, we might not understand much about logs yet, and I don't blame you. But remember, inverses, we can switch these ordered pairs. So I don't have to know much about the inverse. I can switch the ordered pairs. So this would be 1/4 negative 2. This would be 1/2 negative 1. This would be 1, 0. And then we have 2, 1, 4, 2, 8, 3, 16, 4. And inverses, everything is inverse. So this exponential has a horizontal asymptote at y equals 0. That means that this logarithm function is going to have a vertical asymptote at x equals 0. So there's a vertical asymptote at x equals 0. When x is 1/4, we've got negative 2. When x is 1/2, we have negative 1. When x is 1, we have 0. And then 2, 1. And then 4, 2. And then 8, 3. And it's going to get really close to this vertical asymptote but never touch it. And that's the graph of the log. And you can see it's symmetrical about the line y equals x. Okay, so how do we get from exponential form to this log function? Well, again, it's because they're inverses. So if we have y equals b to the x, and we want the inverse, remember what you do is you switch the x's and y's, which becomes x equal b to the y, which is what we have here. And then we can convert this. This is exponential form. And you have to memorize this. You take the, I'm going to write it this way because it's how I think. The log, I'm going to turn that exponential into a log. The base is b. All right. Of x equals y. which is y equals log base b of x. That's converting from exponential form to log form. Now let me say that in a way that's going to help you memorize it. I memorize it this way. There's lots of different tricks you could have, but I remember it this way. A logarithm is an exponent. A logarithm is an exponent. So when I'm doing converting, I know this is the base, and I know when you do have a log, that's where the base goes. So that's not hard. Okay. This exponent can't go here. I always think to myself, a log is, equals means is, an exponent. So the exponent always goes on the other side of the equal sign. All right. So that's how I remember it. A log is an exponent. So if I'm trying to go from exponential form, base to the exponent equals a number, to convert into log form, that's going to be the log base of the number equals the exponent. A log is an exponent. So if we have an example here, this is exponential form. 3 is the base, 2 is the exponent, 9 is just the number. So if I want to rewrite that in log form, that's going to be the log base 3 of 9 equals 2, because 2 is the exponent. So the log base 3 of 9, that's an exponent. That's 2. All right, remember negative exponents? I threw that in here to help you remember. 10 to the negative 3 is the same as 1 over 10 cubed, or 1 over 1,000. So that's a true statement. But now that we've gone over that, let's rewrite that in log form. So that would be log base 10 of what? Not negative 3. The log is an exponent. It goes on the other side. So it's log base 10 of 1 over 1,000 is equal to negative 3. All right, try these and see if you get them without help from me, and then check your answers. All right, how did you do? So this is log form. Log base 7 of 9 equals x. So to convert that to exponential form, the 7 is the base. A log is an exponent. 7 to the x equals 9. This time I'm giving you exponential form. 3 to the 4th power equals 81. Written in log form, the base is 3. Log base 3 of the number 81 equals the exponent 4. A log is an exponent. Log base 6 of 6 to the 7 equals 7. The base is 6. The 7 is the exponent. 6 to the 7 equals the number 6 to the 7. Exponential form, 2 to the negative 3 equals 1/8. That's the base. So log base 2 of 1/8 equals negative 3. A log is an exponent. So the exponent always goes on the opposite side of the equal sign. The last one, log base 25 of 5 equals 1/2. The base is 25. 2 to the 1/2 power equals 5. Okay, so we've gone over converting exponentials to logs and logs to exponentials. Now let's talk about a couple of special logs that show up. The first one is the common logarithm. That's a logarithm that has base 10. So if you see just log of x, all right, that means log base 10 of x. So it's understood, kind of like the square root when you don't see 2 as the index. All right, so a base 10 log, for example, the log of 100, if you need to, if you don't see the base, you can put it there. So a log is an exponent. Can you think of what the exponent would be? Or what this log is? What is the log base 10 of 100? Well, we know that log base 10 of 100 is 10 squared. So that must mean that the exponent is 2. All right, the log of 1,000 would be 3, because the log base 10 of 10 to the 3rd would equal 3. The log of 1/10, well, that's the log base 10 of 10 to the negative 1, because 1/10 can be written as negative 1, so it's negative 1. So this is just talking about a common log, but I'm also revealing to you there's a kind of a neat property. I call it the same base property. And that is, if you can get the same number here as here, then everything's going to cancel. The log is just the exponent. So that's what's going on there. All right, and the second type of common logarithm that you're going to have is not called the common log, it's called the natural log, and it comes from, it's the inverse of y equals e to the x, where e is called the natural number. All right, so on your calculator, here's the E button. It's with pi. So if you hit this twice, you'll get an E, and you'll hit enter, and you can see that it's about 2.718. It's like pi. It's an irrational number. That's about 2.72. All right. So the natural log is written ln of x. So ln stands for natural log. So when you see ln of x, it's just a log. It's just that it's the special notation, and it means that the base is e. So you won't see the e here. You just need to know it's there. Okay. So let's take a look at what the natural log of e is. So if I hit this button here, this is your log button, and if you hit it one time, you'll get natural log. If you hit it twice, you get base 10 log. But if you hit it 3 times, you get any base log. Okay, so I want natural log, and I'm going to put e in there. And what is the natural log of e? Well, it's 1, and that's really important. That's a really, really important property that we're going to use when we solve logarithmic equations. But why is that? Well, ln of e has base e, and e has an exponent 1. And so using this same base rule, the natural log base e of e is just 1. So that's an important property. Okay, now that we know how to convert exponential form to log form, we can find the inverse of an exponential. And it says, then state the domain and range of the given function and its inverse. We know how to do that. And then also state the horizontal and vertical asymptotes, if any, and sketch their graphs. Okay, so remember how to find an inverse? We say, well, that's y, and then we switch the x's and y's, and then we have to solve for y, right? Well, converting from exponential form to log form is going to be very helpful if we want to get this exponent, this variable, out of that spot. We can't divide by 4. We have to have a way to get it out of that spot, and the way that we're going to get it out of that spot is to rewrite this. This is exponential form. We want to rewrite it in log form, so you have to remember how to do that. So remember, the base is log, and the base is 4 of something equals what? Well, a log is an exponent. The y goes there, the x goes there. And then we put it y's by itself, just like that. So then we use inverse form. So the inverse of f is log base 4 of x. So we just found the inverse of that exponential, right? Second thing, state the domain and range. All right, well, remember, there's a neat thing that the domain of this function is the range of the inverse. And the range of this function is the domain of the inverse. So you can pick and choose which one you find. Now, the domain of an exponential, you kind of need to know what this looks like. So it says to graph both of them. So I'm going to go ahead and graph the exponential. You should know that if it's not being translated up or down, the horizontal asymptote is going to be y equals 0 for this. And then when x is 0, 4 to the 0, y is 1. And when x is 1, y is the 4th, is 4. And so that's a good enough sketch right there. So that's the graph of f of x equals 4 to the x. So if you can visualize this graph or graph it, you can see what the domain and range is. Well, the domain of an exponential is always going to be all real numbers. but the range is 0 to infinity for this one. So once we have that, then we have this, because the domain of this function is the range of the inverse. And the range of f is the domain of its inverse. And once you get a couple of points, and you know that the horizontal asymptote is y equals 0, then everything switches on the inverse. So this log has a vertical asymptote of x equals 0. And it has points 1, 0, and 1, 2, 3, 4, 1. And we know that it has a vertical asymptote at x equals 0, so it's going to look like that. So we can use the fact that we're comfortable, a little bit more comfortable with the exponential, to get the information on the log, something that we're not as comfortable with. Okay, now, this is time to make it official. This vertical asymptote, x equals 0. I mentioned this in another video, but now I'm going to make it official. It turns out there is another domain restriction. This right here, this spot right here, it can be surrounded by parentheses or not. It's called the argument. And the argument of a log function must be greater than 0. All right, so let me show you. So if I put in, let's do a base 10 common log, log of -3. Does not like that, says domain error. If I put in log of 0, does not like that, domain error. But if I put in log of 5, it'll give me that. So this argument right here, this spot right here, cannot be negative. All right? So let's graph this. So this is f of x equals log base 2 of x minus 3 using inverses. Well, first thing, I'm going to state the domain of this before I do inverses. So you have to add this to your checklist. This spot right here, not x, but this whole spot has to be greater than 0. So I now know x has to be greater than 3. And the way logs work, that means that there's a vertical asymptote at x equals 3. So I'm going to start with that. Then it says use inverses to graph it. So I'm going to create the inverse for this log function. Log base 2, x minus 3. We're going to switch the x's and y's. And then just like before, we've got a problem. We want to get y by itself. But see, it's stuck inside this argument. And the only way you're going to get it out of that argument is to rewrite this in exponential form. So this is log form. Exponential form would be the base 2 to the power of x, because this is the exponent. The log is the exponent, equals y minus 3. So then if we add 3, we get 2 to the x plus 3 equals y. So the inverse of the log function is the exponential function plus 3. So if you want to put a few points in, if I put in 0 for x, 2 to the 0 is 1 plus 3 is 4. So 0, 4, that means that 4, 0 is on my log function. If I put in 1, I get 2 to the 1 is 2 plus 3 is 5. So 1, 5, that means that 5, 1 is on my log function. If I put in 2, 2 squared plus 3 is 7. That means that 2, 7 is the exponential point and 7, 2 is the log point. All right, so if I graph those, 1, 2, 3, 4, 0, 5, 1, 7, 2, and I know how vertical asymptotes work. I'm going to get really close to that vertical asymptote and then go out that way. Now I've graphed the log function. Okay, so hopefully you've gotten more comfortable with logs. So now let's talk about more properties of logs. All right, so the first one we talked about, the log base b of 1 is 0. At least I think we've talked about that. So that's something to memorize. Anytime you've got 1 in your argument, the log base b of 1 is 0. The log base b of b is off of this this property that we've talked about, there's an exponent of 1. And so if we have the same base here and here, that's just 1. So the log base b of b to the x is just x. And that, I give it a name, call that the same base rule. And then this one is a lot more rare, but if you have the same base here, b to the log base b of x, that's just x. Okay, so think about these properties, try these 8 problems over here, and then we'll go back and check. All right, so here we're using the same base rule. Log base 5 of 5 to the 7 is just 7. Here we're using this property of the argument being 1. Log base 6 of 1 is just 0. Here, same base rule again. Log base 3 of 3 of the 1 is 1. Here, 5 to the log base 5, same base here, is just 125. Here, this is a repeat from the other side. The log, if you don't see the base, it's 10. Log base 10 of 1 over 1,000, well, that's the same thing as 10 to the negative 3. So the log base 10 of 10 to the negative 3 is negative 3. Here again, no base, so it's 10. And 100,000 is 10 to the 5th because there's 5 zeros. So the log base 10 of 10 to the 5 is 5. Here, no base, so it's 10. 1/10 is 10 to the negative 1. So the log base 10 of 10 to the negative 1 is negative 1. And then natural log of e is just 1. All right. Now, try the properties again. Now, this time you're going to have to add and use PEMDAS. All right. So use your order of operations. I'll pause it, see how you do. Okay, so how did you do? What I meant by PEMDAS is you have to make sure you follow the order of operations. So first one, you didn't really need to do that. You needed to know how to use negative exponents. So just in case you need a little review, what I'm doing is I'm getting rid of this denominator by using negative exponents. I can move that up to the numerator if I make it a negative exponent. So 1 over 36 is the same as 6 to the negative 2. And so then I have the same base rule. And I can use the same base rule, that's negative 2. All right, number 2, you have to use order of operations. You can't do 5 times 4. You have to do exponents before you do multiplication. So you need to think about that first. So 5 times, and then 4 log base 4 of 8 is just 8 because you have the same base here. And then you can multiply and you get 40. Same thing here. This is an exponent, so we need to take care of that first. In log of 10, there's a base 10 that you can't see, and there's an exponent 1 that you can't see. So that's 1. So 38 times 1 is 38. Here you got 23 times the log base 10 of 1. Anytime your argument is 1, it's 0. So 23 times 0 is 0. And here you got 4.3, you got to do that first. ln of e is 1, so 4.3 is times 1 is 4.3. Okay, so we've talked about a couple of properties. Now we're going to really get into 3 really important properties. Now, one of them is called the product rule for logs, or law, or property. Okay? And it says that if you have one log, base b, any base, and the argument is a product, if you've got something x times y, 2 things multiplied together, one log with a product in the argument is equal to 2 logs with each of those factors in that product split apart. Okay? So I tried to say that correctly, but here's how I remember it. It doesn't make a lot of sense mathematically, but it kind of comes out of off your lips nice. And I say 1 log multiplied is equal to 2 logs added. And if you say that over and over again, 1 log multiplied equals 2 logs added. Now that's terrible math, so just be leery of that. If you've got 1 log and a product in the argument, you can make that 2 logs added with the factors of that product split apart. 1 log multiplied is 2 logs added. All right, so let's see what it looks like when you apply the property. Okay, now there are no directions here. So the directions in this section are really just basically either going to say expand or simplify. And so we're just practicing these logs, right? So expand means to use all the logs that you can until you're done. So until you can't use any more. So right now I've got a product in here. 3x isn't 3x, it's 3 times x. So the log base 2 of 3 times x, applying the product rule, would be the log base 2 of 3 plus the log base 2 of x. Now, we've only learned one rule so far, and the same base rule. So you would then have to look at each of these logs and see if there's any property that we can apply, and there's none. So we're done. Okay, now the other direction would be for me to say simplify or write the following as one log. So here I have 2 logs added. Same base, they have the same base. So 2 logs added, I can write as 1 log with these arguments multiplied together. All right, so if I do a little bit more math, I can distribute that 4 and get 4x plus 8. Now, can you split those apart? No, it's not 1 log added is equal to 2 logs added. See how that doesn't sound right? 1 log multiplied is 2 logs added. So you can't split those apart. Okay, the next rule we're going to talk about is similar. If you have 1 log divided, 1 log with a quotient here, you can write that as 2 logs where this quotient is separated into 2 logs subtracted. Okay, that's called the quotient rule. All right, so here, if you see 1 log with a quotient, you can write that as log base 4 of 3x minus the log base 4 of 4. Okay, now this is where it gets tricky because you have to keep going if you can. So now we have a few more rules in our disposal. So look at this log. What do you see in the argument? Do you see 3 times x? Well, 1 log multiplied, you can split that into 2 logs added. So that would be the log base 4 of 3 plus the log base 4 of x. So that log becomes those 2. Then, do you notice this one? You see this is really hard for students. You gotta always be on the lookout for the same base rule. See the 4 base and the 4 base and the understood exponent of 1? Turns out the log base 4 of 4 to the 1 is just 1. So you have to keep applying the properties until you can't apply anymore. So this log you can't do anything with, that log you can't do anything with, and then you have minus 1. All right, let's use the quotient rule going the other way. 2 logs subtracted is equal to 1 log with those numbers divided. And notice that the positive log argument 15 goes on top. The negative minus 1 to 3 goes on the bottom. You can simplify that. That's natural log of 5. All right, and then the third rule in this kind of cluster is called the power rule for logs. All right, so if you have 1 log base b of x to the p power, then you can take that p, that exponent, that power, and put it in the front, p times the log base b of x. Okay, so if you have the log base 3 of x squared, you can rewrite that as 2 times the log base 3 of x. All right, but really we're going to use it this way more often because it's kind of like isolating the radical or isolating the absolute value. You're going to want to isolate the log. So really don't want that 1/3 there. Well, the product rule says if you have a number times a log, you can put that number as a power in the argument. That's the power rule. And again, this is tricky because we're not done yet. Because you can simplify 8. 8 is 2 cubed. So it's really hard to teach this. I call it number sense. When I see base 2, I automatically start thinking, is that a base 2 number? Yeah, 8 is 2 cubed. So I can actually keep going here. So log base 2, 8 is 2 cubed. But 8 is being raised to the 1/3 power. So then that means the rule here, if you got an exponent to an exponent, you just multiply. So that means that that's 2 to the 1, because 3 times 1/3 is 1. Well, then that means that you got the same base here and here, so the log base 2 of 1 is just 1. So that simplifies all the way to 1. And furthermore, you could have done this differently. Maybe you noticed that right off the bat. Maybe you said, okay, 1/3 times the log base 2 of 2 cubed, that's 1/3 times 3. So either way. All right. And the last one is kind of been a property that's gotten obsolete because of our calculator. But it's called the change of base rule. And it says that if you have the log of any base, log base b of n, you can change it to the log base x, whatever base you want, of n divided by the log base x of the base. Now, that's confusing to students because you can really use any base you want. But what are our favorite bases? Well, 10, the common log. So most people memorize it this way. The log base b of n is equivalent to the log of n over the log of b, or the natural log. The log base b of n is equivalent to the log of n divided by the log of b. All right, so it's kind of a historical, it's archaic because we used to not have calculators that could do any base log. So you had to change that to log of 5 over log of 3. All we had was base 10. But see, now with our calculators, again, this is our log button. If we hit it 1, 2, 3 times, we actually can put any base we want in. So log base 3 of 5 would look like that. And you'd get 1.4650. Let's see what this gives me. So if I do base 10 log, hit it twice, log of 5 divided by base 10 log of 3, see, I get the same answer. Then if I do ln, which you just have to hit the button once, divided by natural log of 3, you still get the same answer. So that's the change of base rule. All right, so here are some common mistakes people make. So I do continue to teach the change of base rule because it helps me say this log of 6 divided by log of 2 is not log of 3. You can't do that. The log of 6 divided by log of 2 is actually the log base 2 of 6 according to the change of base rule. And that's not the same thing as log of 3. And then the other thing, the reason I say 1 log multiplies 2 logs added is to keep people from doing this. People want to split this apart all the time. But in algebra, addition is actually more like glue. 1 log added is not 2 logs added. That makes no sense. You cannot simplify that. That's as simple as you can get it. You can't pull those apart. And then this is pretty rare. This would be something that might happen in calculus. But the whole log base b of x to the 2 is log base b of x times log base b of x. This is log base b of x squared. So there's a difference between that 2 just being in the argument and that 2 being outside the whole log. Okay, so those are common errors. All right, let's practice these, and I'm going to practice these 2 definitely, and then I'm going to actually practice a few more because sometimes we need a little bit more examples. But you can pause me at any time and try it yourself. All right. The first example that I'm giving you, I have to state the following. We don't use radicals when we do logs, so you have to really remember this. The nth root of x to the n, that's radical form, is x to the n over n. That's rational exponent form. So remember, the index goes in the bottom and this power goes in the top. All right, so the first thing we have to do here is rewrite that using this rule. So that would be the log of x squared plus 5. And that whole thing is underneath there, so that has an understood 1. So that's going to be x squared plus 5 to the 1/5. Okay, so that's not a log rule. That's just we can't use any of our log rules until we get rid of the radical. So we have to rewrite it. Okay, now we can use the rule. This power can go in the front. That's the power using the power rule. So that would be 1/5 times the log of x squared plus 5. Then you have to say, okay, am I done or can I do another rule? Can I expand that? No, no, no. You can only expand when you see multiplication or division in here. So that one, you're done. All we had to do was use the power rule. All right. Now this one's got a little bit more going on. So you have 7 times log base 5 of c plus 1/8 times log base 5 of a plus 1/8 times log base 5 of b. And you're asked to simplify. So what that means is we want to condense that into one log if we can, because they all have base 5. So we're going to be able to write this one log. So you have to know the order in which you do things. Well, you have to isolate the log before you can use the product rule or the quotient rule. What I mean by that is you got to get rid of the 7 that's being multiplied. So the first thing we're going to do is we're going to use the power rule to do that, to get those logs isolated. So that would be the log base 5 of c to the 7th. Plus, that would be the log base 5 of a to the 1/8 power. Plus, that would be the log base 5 of b to the 1/8 power. So we use the power rule there. Okay, now we have actually 3 logs added. And the product rule says if you have 2 logs added, that's 1 log multiplied. Well, it turns out you can do as much as you want. If you have 3 logs added, you could write that as 1 log with these arguments multiplied. So that's going to be the log base 5 of c to the 7th times a to the 1/8, not plus, times b to the 1/8. So we're changing from addition to these arguments being multiplied. And that's that. Okay, flip over to the next page and you see the exercises that I was talking about. And so I want to do a few of these. So I'm going to zero in on number 3 and maybe number 4, but I want to do it real time. So I'm going to copy the problem 3 and do it over again. All right, so the directions here are to expand. And I'm going to do this the long way, but then I'm going to show you another rule that I call Miss Mills combo rule. But let's do this the long way. So what do you see? I see 1 log divided. 1 log divided is 2 logs with the arguments split, 2 logs subtracted. Right? Does that make sense? That's the quotient rule. Okay, so you had 1 log divided, that's 2 logs subtracted. All right, now, then you have to look at each individual log. By the way, people ask, when do you use parentheses and when do you not? It's up to you. You know, you can use parentheses to guard your argument if you want. All right, but anyway, you have to look at each log individually. So look at that log, do you see a product? All right, so we have to expand, so we have to use the product rule. So that's going to be the log base 3 of 9 plus the log base 3 of x to the 5th. All right, does that make sense? All right, now there's a minus here, and this is tricky. You have log base 3, and do you see a product in here? Now we have to use the product rule. This is what's tricky. The negatives are always tricky. That 1 log is getting ready to become 2 logs. That minus belongs to that 1 log. So when that 1 log becomes 2 logs, you need to make sure you use parentheses. So that's going to end up being the log base 3 of y plus the log base 3 of y to the 4th. And when people forget to use the parentheses, they forget that you've got to distribute that negative. So this is actually log base 3 of 9 plus, I'm going to use the power rule right here, 5 log base 3 of x, distribute, minus log base 3 of y, minus log base 3 of z to the fourth. All right, I'm doing this extremely the long way. All right, now let's go ahead and deal with this. Now we have 4 logs we have to deal with. This 9, and this is base 3, you got to learn to see that 9 as 3 squared. So that's just 2. I already used the power rule on that one. Got a little ahead of myself. This one's done. There's nothing you can do about that. But what can you do about this one? Power rule, minus 4 log base 3 of z. I think that's everything we can do. All right. Now, are you ready for the shortcut? All right, Miss Mills combos rule. Miss Mills combos rule. Combo rule. All right. If you have a bunch of, let's call this x, y, w, z. If you have a bunch of products and quotients, so you've got x times y, y times z, and this divided. Multiplication and division are inverses of each other. And we know that 1 log multiplied is 2 logs added. And we know that 1 log divided is 2 logs subtracted. So what we can do is we can just use one rule here, and it's going to be this. Log base b of x plus the log base b of y minus the log base b of w minus the log base b of z. All right, let me explain. What you can do is you know that multiplication and division is going to expand to a bunch of different logs with addition and subtraction. The numerator products are going to be positive, and the denominator products are going to be negative. Okay, so if you know that rule, it's going to keep you from having to worry about distributing. See, look, go back and look at this. And I got a little ahead of myself here, so I'm going to take this 5 and put it back so you can see it a little bit better. So this example, you see how you have 9 times x to the 5th divided by y times z to the 4th. I could, using Miss Mills' combo rule, go just all the way down here, because that's going to become log base 3 of 9 plus the log base 3 of x to the 5th, because they're in the top, they're in the numerator. And this y and the z to the 4th are in the denominator, so that's minus log base 3 of y minus log base 3 of z to the 4th. So that's Miss Mills' combo rule if you're interested in using that. All right, let's do one more. Let's look at number 4, the log base 2, the square root of 8a cubed. All right, so remember we can't use square roots. So what we have to do is we have to take this whole thing underneath that as an exponent of 1, and we have to rewrite that as log base 2 of 8a cubed to the 1/2 power. And we want to expand, so this is going to be, use the power rule, so that would be 1/2 times log base 2 of 8a cubed. Well, now we have a product in here. So 1 log multiplied is 2 logs added, but same issue. You've got this 1/2 times that 1 log, but that 1 log is getting ready to be 2, so you got to use parentheses. This is going to be log base 2 of 8 plus the log base 2 of a cubed. Okay, so that would be 1/2 log base 2 of 2 cubed plus 3 log base 2 of a. Power rule. Same base rule, that's 1/2 times 3 plus 3 log base 2 of a. Distribute the 1/2. 3 halves plus 3 halves log base 2 of a. So make sure you do all of these practice problems here and check the key. On the back, you have to expand, to simplify. So let me pick one from there. All right, I picked number 2. It says rewrite each of the following as a single logarithm. So I picked number 2 because you're a seated, you can't ask me a question. So this is tricky. So all of these are natural logs. So a clever way to get rid of this one that stands out different than that is to remember that ln of e equals 1. So I can rewrite that as ln of e. All right, now I want to write this as a single logarithm. So before I can use the product and quotient rules, remember I can't have any number in front. So I got to use the power rule for this. That would be the natural log of f cubed. And the power rule for that would be the natural log of h squared. All right, now, do you see how you have 4 logs added and subtracted? You can use Miss Mills' combo rule. 4 logs added and subtracted is going to be 1 log with things in the numerator multiplied together and things in the denominator multiplied together. These 3 are positive logs. So they're going to go in as f cubed times g in the top. This is a minus ln of h squared, so that h squared is going to be in the denominator. And that's it. You're done. So practice the other 3 on the back, and you can use the textbook to practice some more and WebAssign. Just practice your logs. You'll get more comfortable with them.